Hello. Thank you for listening to our talk about our proposal title, Accelerated Burn-in Process for High-Power Quantum Cascade Lasers to Reduce Total Cost of Ownership, sponsored by NavAir. Adtech Photonics manufactures quantum cascade lasers, or QCLs. These are key components used in infrared countermeasure systems. Adtech is a proudly woman-owned business that was significantly involved in the early commercialization of QCL technology in 2005 and was unique in achieving this within the United States, in particular at commercial scale. We have been instrumental in the development of high-power lasers, focusing on large-scale, high-quality, and low-cost production. Located in the Los Angeles area, we have an 11,000 square foot facility fully equipped for 3 to 5 semiconductor fabrication. This is ideal for full control of the laser manufacturing and assembly of our products. The advantage of this QCL technology is the ability to tailor the laser's frequency to any target wavelength in the mid-infrared region, which is wavelengths from 3.5 microns to 13 microns. Adtech was one of the first companies to commercialize QCLs and has been manufacturing them since 2005. Over our history, we have achieved several significant milestones in QCL development. Emitting at 4.8 microns, from a single facet, we're able to achieve greater than 2.8 watts of output power under continuous wave operation at room temperature, with a wall plug efficiency of 12.5%. We've also developed QCL arrays, capable of pulsed or quasi-CW operation, with power over 20 watts. Additionally, we've shown world record WPE of 50% at low temperature, and room temperature CW operation of 1.7 watts at 7.3 microns, 1.1 watts at 9 microns, and 0.8 watts at 9.5 microns. Adtech's quantum cascade lasers are designed to emit in the mid-infrared region between 3 and 12 microns. With our focus on QCLs, we develop and supply lasers for many types of applications and systems in the market. Some QCLs are manufactured to hit only a single precise frequency. Others are manufactured for wide tunability for use in external cavity systems. Some of the more interesting applications require very high-power lasers at precise wavelength ranges, which is what we provide. You can see in this technology's milestone timeline where we come into the scene in 2005. Adtech was the first commercial company to demonstrate MOCVD growth of a QCL wafer. This highlights the shift in technology that allowed QCLs to be manufactured in a high-volume production environment. At Adtech, we have 3 MOCVD reactors, with each reactor capable of multiple wafers per run, as well as performing the additional regrowth steps necessary for a full production cycle. Adtech has been working on QCLs for almost 20 years, and along the way has achieved many milestones, some so far only of academic interest, for example, terahertz lasers based on QCL technology, while others offer enhanced efficiency, power, or array use, and have yielded real-world interest and utility. Right now, arrays are at the leading edge of QCL technology. Adtech has been providing non-coherent arrays for a few years, useful in situations where raw power is good enough, for example, some large-volume sensing, and is currently working on coherent beam combining for the most demanding applications, like IRCM, that require an extremely bright low-divergence beam. While QCLs have a variety of potential uses, most use cases have yet to go into high-volume production because the devices are expensive. The expenses arise for many reasons, but one of the key reasons is testing. The cost of validating that each laser is reliable and will survive its target lifespan is substantial. In the past, the only way to achieve this validation was to run each laser through a long burn-in process and hope that this would cause most of the imperfect devices to fail. To improve this situation, we are exploring whether machine learning techniques will more efficiently help predict device failure. With this algorithm, we hope to predict early failures and thus save hundreds of hours per laser of quality analysis and reliability testing. This also saves hours of labor for replacing failed parts and reduces the amount of maintenance required, as well as the cost of replacing failed devices. This improved process, at a minimum, will reduce high-volume costs by half and can potentially present a 5-fold cost reduction over non-machine learning-assisted technology in large-volume applications. The hope for the current program is that it can improve overall performance and costs. This may occur not just in the most obvious ways, like preventing the shipment of many lasers that might have failed in the field and reducing the costs of the current, very long, burn-in times, but also by allowing for earlier detection of problems in the manufacturing process, excluding unpromising sections of a wafer from processing, and avoiding mounting diced lasers that appear prone to failure. The approach chosen makes use of support vector machines. We've provided a large number of lasers to be tested, yielding over thousands of hours of data per laser. These are repeatedly tested, characterized, and stressed, often to the point of failure. The resultant data is fed into a machine learning model, which detects patterns in the failure data, so that early, easily measured features can be used to predict later failure. There are many data points collected, and we're looking into which parameters are the key factors to monitor going forward. This should allow for accelerated burn-in, whereby a rapid battery of stressors can be applied to a QCL, the results measured, and a reliable prediction made as to whether the device should be deployed or discarded. An additional side aspect of the project is understanding and characterizing various failure modes, so that subsequent QCL designs can try to limit and control the drivers of failure. While the project is currently ongoing, the risk level defined is all low. We are making great progress and have committed a lot of time and resources to achieving the goal of this topic to match the expected schedule. No serious, unforeseen problems have been encountered. To summarize, quantum cascade lasers are useful for detecting various types of chemicals, which primarily requires very accurate wavelength control, and infrared countermeasures, which require coherent, low divergence, high-power lasers at precise wavelengths. Single emitters are capable of over 2 watts of output power. When more power is required, QCL arrays present a high-power solution with reduced cost, size, and weight. Selling a reliable laser is very important for our customers. This is currently achieved through high-stress burn-ins for long-term reliability, but this is undesirably time-consuming and expensive. Enhancing the manufacturing process with machine learning would provide end users with a great deal of value. It would not only reduce production cost and time, but also the post-production maintenance costs. Apart from military applications, QCLs have been sold commercially for about 2 decades and have achieved market acceptance. Use cases that may be of particular interest include free space sensing, spectroscopy, and gas detection for various chemicals. Adtech already sells to a range of companies, including large scientific instrumentation companies, as well as prime contractors. We keep these companies informed of new capabilities we have achieved. For example, new wavelengths, or new capabilities like broad tunability and arrays. Our hope and expectation is that the cost reductions we are able to achieve from accelerated burn-in will in turn result in larger orders from these companies. The primary investigator for this topic is Dr. Xiaojun Wang. For business inquiries, please reach out to us at sales@atphotonics.com.